Okay. Some result from Laplace transform will be useful here, but I am not going to prove them. Suppose x a t has got Laplace transform x a s, and region of convergence normally, like in the case of Z transform, we used to write mod Z within some. Here it is real part of S, that is sigma only matters within some range, sigma 2 to sigma 1, like that. This is how we denote. But anyway, some ROC. I am not writing the ROC here, but some ROC. Then dx a dt, its Laplace transform is given by s times x a s minus this function at t equal to 0 minus. So, it is initial condition. Okay. At 0 minus, it is initial condition. But I am considering that signal system all will be switched on at t equal to 0, t equal to 0 minus they are 0. So, at 0 plus t equal to 0 plus signal comes and all that. So, this x a t. Now, if we assume 0 initial condition, that is if we assume this to be 0 initial condition, then this is equal to just s x a s. Then d square dx a dt square. This is d dt of this one. So, it will be s times s x a s minus that at t equal to 0 minus. I am giving the general result. S times the Laplace transform of dx dt, the dx dt is this that I am writing, minus this quantity dx a dt at t equal to 0 minus. Under 0 initial condition, this will be 0, this also suppose is 0, then it will be equal to only s square x a s, so on and so forth. Okay. Now, consider a differential equation, a system an analog system which takes x a t gives an output y a t, a particular system which is governed by a differential equation. In the case of sequences, we had difference equation, it is differential equation, but treatment is same. Differential equation is maybe say dp y. For the time being, I am dropping the subscript a. It is all analog, so no point in carrying the subscript a. dpy dtp multiplied by ap, then ap minus 1 dp minus y. So, derivative pth order, p minus 1 is order, dot dot dot, plus a 1 dy dt plus a 0 y t is given by b 0 x t plus b 1 dx dt plus dot dot plus maybe b q dq x dt q. This equation will have two solutions. In fact, this equation is given and you need initial conditions. These initial conditions are given, that is system is switched on at t equal to 0. Okay. Input is 0 at t equal to 0, input starts its value from 0 plus. So, at 0 minus, at the point of switching on, input is 0 and then it picks up. Okay. And these conditions are giving, these initial conditions, this value at 0 minus, dy dt at 0 minus, dot 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 up to this. Okay, these initial conditions are given. Now, like the difference equation we had considered earlier, the rational model, here also there will be two solutions. One is called the steady state solution, one is called the transient solution. Steady state for transient solution, you take the right hand side to be 0, that is no input is given, and solve the equation with right hand side 0, solve it, and there you plug in all the given initial conditions, and you get a solution transient. So, y capital T, T for transient, T r for transient T. Okay. So, if you put y T r T on this side, that will equate to 0, and that will satisfy all the difference, all these initial conditions. Another solution is steady state solution, y s steady state T. Here you assume the initial conditions to be 0, give the input is 0 at t equal to 0 minus, and then it starts picking up, and then solve it. That solution is given purely by input only, no initial effect of initial conditions, that is called YSST. Then our claim is total solution is a summation of the two, YT anymore is a summation of the two. That is very easily seen, like as we have seen in the case of rational systems, because if you put this on the left hand side, then you take out the YT or T part, that part, that is A0 YT or T, A1 dyT or dt, AP minus 1 dP minus 1 YT or dTP minus 1 dot dot dot. That part will be equal to 0, because that is how the solution was found. The right hand side was made equal to 0, left hand side was solved, initial conditions were used, and we got the solution YT at T. Therefore, if YT at T is put back on the left hand side, I will get equal to 0. So, out of this, if we take out YT at T component separately, A0 YT at T, A1 dyT r divided by dyT r dt, and so on and so. So, that part will contribute nothing, that is giving us to 0. And if you take out the YSS part, A0 YSS T, A1 dySS dt, AP minus 1 dP minus 1 YSS dTP minus 1, and dot dot dot. That will equal to this, because that is how the solution was obtained by equating left hand side with right hand side. So, therefore, left hand side, overall left hand side will be equal to right hand side. Component contribution due to YT or T from the left hand side will be equal to 0, because that is how the solution was obtained by keeping only left hand side and equating right hand side to 0. So, if you put back that solution, that part gives rise to nothing, and when you put back YSST on the left hand side, that will give rise to the right hand side. So, this equation will be satisfied, and when you go to T 0 minus YSST, that will be 0, because when that time there was no input at 0 minus, and when there is no input, there is no output. But YT or T at T equal to 0 minus, this solution, this will satisfy all those initial conditions, because that is how this solution was obtained. Okay. The solution was obtained by solving this differential equation with left hand side in place, right hand side 0, and with all initial conditions given in. So, therefore, YT at T will satisfy all those conditions at T equal to 0 minus. Okay. And YSST and all its derivatives, they are zeros. So, they will not contribute anything, but overall summation will equate to this initial condition. So, that also will be satisfied. Then, as I told you, in the case of rational model, because of the presence of this, system will not be linear and shift invariant, time invariant, because suppose input is delayed. If input is delayed, say suppose instead of switching on the system, if instead of giving the input, I switch on the system at t equal to 0, but 0 plus, but instead of giving input at that time, suppose I give input after t amount of time, then till that time system will be at rest, because there is no input. All right, there is no input. I am talking of YSST only. Okay. Suppose initial conditions are not there, I am just bothered about YSST. So, there is the initial condition, system is switched on at t equal to 0 plus, but no input is given at 0 plus, input is given after t amount of time. So, till that point of time, system will be at rest, because there is no input, there is no initial condition. So, after the t amount of time, I will start getting the same output which I was getting earlier. So, then now the new output will be nothing but of the same form as the previous output, but separated by amount of time, delayed by an amount of time. So, it will be, that means it will be shift time invariant. If input is delayed by t, output will be delayed by t, and it is linear, very easily seen. Okay, because instead of giving x1, suppose I give x1 t, I get a solution. I give x2 t, I get another solution. It is very simple, easy to see then if I give x1t plus x2t or a linear combination C1 x1t plus C2 x2t, the output will be C1 y1t plus C2 y2t, because if you put that on the left hand side, that will equate the right hand side. So, YSST alone, that is when initial conditions are 0, YSST alone satisfies linear and time invariance. But this part, it is given purely by initial conditions, right. Now, suppose both are non-zero initial conditions are present, I switch on the system at t equal to 0 plus, but give the input after t amount of time. Then what happens? Contribution due to this will be delayed. If xt is delayed by t, this will be delayed, this part, this we have already seen. This part is obtained by keeping the input initial conditions 0 and solving this, and that you have seen this will be delayed. But this will not be delayed, because this is not derived from the input, this is derived from the initial conditions. The moment you switch on at t equal to 0 plus, initial conditions will come in, right hand side is 0, this solution will be there. So, this will continue to be same as before. So, this summation is not a delayed version of this summation, this is delayed by the same amount of t as the input, but this remains as it is. So, overall YAT here, overall output here is not a delayed version of the previous overall output by amount of t. That is why it is not time invariant. Then again it is not linear, because I give x1 t as input, okay. I give x1 t as input, I get yt at t plus say yss, some yss in t. I give another input, I get the same thing yt at t plus another yss t. If I add the two input, okay, I will not get summation of the two output, because output will be still yt at t plus, it is like this, let me explain. Suppose I have got x1t alone give rise to yss1t, the steady state component, that is keeping the setting the initial conditions 0 and solving, you get this. Suppose I give x2t, the steady state component is this. When the initial conditions are present and I give x1t, output will be yt at t as before plus yss1t, right. Input is x1t, so total this is the output. This is, and when I give x2t, output is still yt at t plus yss2t. If I just add the two, if I give this as input, steady state solution, that will be summation of the two, because that part is linear, we have seen. So, that will be yss1, but this will not get added, because this is independent of input, this is given by the initial conditions. So, input is now this total thing, so its corresponding steady state solution will be the summation of the previous two steady state solutions. That will get added with just one yt at t obtained by, derived from or coming from this, driven from these initial conditions. So, this overall solution is not summation of these two, because if you add the time, it will become, add the two, it will become twice yt at t, but here I have only one yt at t. That is why it is not linear, not time invariant. But if I set the initial conditions to be 0, then yt at t is 0, there is no solution, is purely YSST, and we have already seen YSST, it satisfies both linearity and time invariance. So, henceforth we will consider this differential equation only with 0 initial condition, and under 0 initial condition we have seen, if I take Laplace transform of y, it is ys. So, for dyt it will be sys, for d square y, d t square it will be s square ys dot dot dot. So, I repeat again, I will now consider 0 initial conditions, that is yt at t 0 minus equal to 0, dy dt at 0 minus equal to 0, d square y dt square at 0 minus equal to 0 dot dot dot. Under this we have seen there is no transient solution, because that comes only from initial conditions. If initial conditions are 0, this will be 0. So, there is no transient solution. Solution will be purely the steady state component governed by the input, given input, and then the system is both linear and time invariant. So, it will be linear and time invariant system, and therefore, if you give a delta at the input and record the output and call it impulse response, then another way of obtaining the output will be convolution between these two. Okay. Under this case, system is linear and time invariant because there is no transient solution, initial conditions are 0. Under this case, if I apply Laplace transform of the left hand side and right hand side, what will we have? If I apply Laplace transform here, AP, it will here it will be A0 YS, here it will be A1 SYS, dot 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 dot. Next one, if it is A2 d square y dt square, it will be A2 S square YS, dot 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 up to here AP s to the power p YS, and here it will be B0 XS, then B1 SXS, then maybe B2 S square XS, dot 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 BQ s to the power q XS, right. So, YS you take common, XS you take common, and you take the ratio. You take the ratio, you have equal to A0 so it is a ratio of two polynomials in S, that is why it is a rational form. Okay. Numerator polynomial, denominator polynomial. Now, what is YS by XS? We have seen one thing, that under linear time invariant condition, YAT is a linear convolution between H and X. H A tau X A, okay, I am again bringing Y A, forget about the A part, all are analog, so drop A, T minus tau d tau, tau T is from outside, fixed from outside, these are convolution. So, if you take the Laplace transform of Y, it will be Y t to the power minus S t dt from minus infinity to infinity. So, you will have this thing integrated. This overall integral is a function of t only, tau goes out of integration here. So, it is minus infinity to infinity, this inner part h tau x t minus tau d tau, this is the part here which is y t, and then this into that e to the power minus s t, this is your y t. And then the two integrals can be interchanged, because two summations can be interchanged always, that is the next step. So, outer integral now will be with respect to tau d tau, and h tau depends only on tau. So, this can go outside as common, and this remains inside x t minus tau e to the power minus s t. T I can write as t minus tau dt. So, I have brought in e to the power minus s into minus tau, that is e to the power plus s tau I have brought in. I have to cancel it by e to the power minus s tau, that I can bring, because it depends only on tau, I can bring back here. So, inner integral t minus tau, if you call it t1. So, x t1 e to the power minus s t1, and limits will be same, minus infinity to infinity, because if t goes to minus infinity, t1 goes to minus infinity, if t goes to plus infinity, t1 goes to plus infinity. So, this entire thing is Laplace transform x a s, that goes outside, and this is again Laplace transform of h. So, in time domain convolution means in Laplace transform domain they are multiplied, x a s h a s, which means under linear and invariant, under linear and time invariant condition, YS output Laplace transform by input Laplace transform is the, forget about A, this is HS. Now, for the differential equation based model, which I call rational model, under zero initial condition, we got this ratio YS by X is equal to this, but under zero initial condition also you have seen system becomes linear and time invariant. In that case, YS by X is also equal to HS. HS is the Laplace transform of the analog impulse response. and this is called the transfer function. Okay. So, that means under for rational models under linear time invariant condition, transfer function Hs is given by this kind of form. This coefficient actually come from the differential equation, it is a ratio of two polynomials. Okay. Now, you see this polynomial, numerator polynomial I write n of s and denominator polynomial d of s. Now, n of s let it be as it is, but denominator polynomial I can factorize in first order factors. It is a polynomial in powers of s. Okay. It could be, you can take out AP out, so A0 by AP, A1 by AP, so there will be a 1 by AP factor. Okay. So, 1 by AP factor is some constant factor, say capital A. So, that s to the power p and then some constant into s to the power p minus 1, some constant into s to the power p minus 2, A1 by AP into s, A0 by AP, like that. Okay. So, s to the power p has a coefficient 1, and then if you factorize, all of them will have s only, that is coefficient with s will be 1, s minus maybe some pole alpha 0, s minus alpha 1 dot 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 s minus alpha p. I took AP out, 1 by AP I called capital A, and therefore, s to the power p has a coefficient 1. That is why when you multiply these factors s to the power p will have with coefficient 1, that is the reason I did it. Okay. Every factor gives rise to one pole. Suppose s equal to alpha 0, at s equal to alpha 0 could be complex, could be real, in general complex, alpha 1 could be in general complex. At s equal to alpha 0, this factor is 0, and therefore, there is division by 0, so this transfer function does not exist. So, this transfer function does not exist, this function at these poles. Therefore, ROC of such a function cannot contain these poles. Therefore, ROC could be like this. If you draw the poles, given such a rational function, suppose you draw the poles in the S plane, suppose there is a pole here, there is a pole here, there is a pole here. You draw vertical lines. Now, these poles cannot be part of ROC. At the same time, you have seen that for linear time invariant systems, ROC of a Laplace transform will be governed by what? I mean, strips. So, those strips, the vertical strips, like there could be vertical strip. This vertical strip should not contain any pole. So, suppose I start from this line just to the right of the line, and if I consider any strip or go further, widen the strip, go on up to infinity. Since there is no pole, this entire region up to infinity can be one ROC. Or then I consider the line between these two, this zone between these two lines, this is one strip. This strip does not contain any pole because I am not including the lines, that could be one ROC. ROC cannot contain the poles because at poles the function does not exist. Or it could be this strip, but without including the lines, that could be one ROC, or that could be another one going up to minus infinity, that is an infinite strip. Okay. Now, for the system to be causal and stable, I have seen, we have told, we have already explained that ROC should start from a vertical line to the left of the j omega axis and go entirely rightward. That is possible only if all the poles, suppose there are 3 poles, all the poles on the left hand side of the j omega axis. Then I consider the one which is closest to the j omega axis, draw a vertical line, and then consider this. This will not have any pole because all the poles are assumed to be on the left hand side of the j omega axis, and I am taking the one closest to the j omega axis, drawing a vertical line through it and going rightward. So, this zone contains j omega axis and it is going to the right side of a vertical line. So, it will be both causal and stable. So, that means all the poles must be on the left hand side of the j omega axis. That side is called LHP, left half plane in the S plane. So, all poles for a linear and time invariant, for a causal and stable rational system, all its poles must be on the left half plane, and you take the one closest to the j omega axis and draw a vertical line through it and then go to the right side. From that, it will include j omega axis and it is going to the right hand side of a vertical line. So, it will be both causal and stable. Therefore, in designing analog filters, you make sure that you design these coefficients, these coefficients AP minus A1, A0 not only to have some desired frequency response, but also to make sure that the resulting poles are all on the left half plane. Okay. Keeping these two in mind, and other thing is, as I told you, that if there is a rational system, these are H's, okay, and these coefficients are coming from the differential equation, but differential equation I am not going to. Suppose you are directly designing them. Okay. How will you designing them? One condition is that it should give rise to poles which are all within in the left hand side of the S plane, that is to the left of the j omega axis. Okay, that is must. Other considerations are this. If there are other consideration is what will be the frequency response. Frequency response means S will be replaced by j capital omega, that is sigma is 0, which means in the S plane I am on the j omega axis for which sigma is 0. So, I am not moving on the entire S plane, I am moving only on the one line, that is the j omega axis, y axis, and there if I take S, that is equal to j omega, replace this, you have B0 plus B1 j omega, B2 j omega square, so, this is a function of omega. Okay, this is a function of omega. So, this will be your transfer function. Okay, this is a complex number in general. Any Fourier transform is a complex number. This is a Fourier transform of the analog Fourier transform of that analog impulse response. This was the more general transform, Laplace transform. This is a Fourier transform. You take mod of this and square, so that will be magnitude square. You take the phase of this, all those things are there, right? So, this will give you if you take the mod square of this will give you the magnitude response. If you want a good filter, you have a specified or you have a desirable frequency response, try to design the coefficients, so that if you plot this mod square of this versus omega, you go close to whatever was desirable. That is one consideration, but make sure your choice of A0, A1, A2, AP are such that the poles are all on the left half plane. That is, real part of any pole alpha should be less than 0. And one more thing, if suppose these coefficients A0, A1, AP, they are all real, suppose A0, A1 dot 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 AP all are real, then either there will be a real pole or there will be a complex conjugate pole. That is, if there is a pole at alpha, there must be at alpha star. So, that you have S square minus alpha plus alpha star S plus mod alpha square. This is real and this is real. Alpha plus alpha star means twice the real part and mod square. Okay. So, that is another thing, that if you have coefficients that are real, then either you will have real pole or you will have conjugate poles. If suppose you have got second order pole here, S minus alpha square, and alpha is complex, then its conjugate also must be second order. So, that we have got S minus alpha star, you get a polynomial, another S minus alpha star, another polynomial, both second order and both have real coefficients. With this, we will consider analog filter design, in particular Butterworth low pass filter design, okay, how to derive that expression, all those things there. And then we will try to move to the digital filter design. We will show that similar treatment cannot be carried out there because of some problem. And then we will show how to design this IR filters, digital filters, by taking recourse to analog filter first. Okay. That is all for today. Thank you very much.